Good morning. This video is meant to take the place of our Friday, November the 15th classes, pre-calculus classes. I'm going to start where Section 8 left off yesterday because they didn't get quite as far as Section 6. So those of you in Section 6 may find the first couple of minutes of this to be a review, and you can fast forward if you would like to. So we left things here on Thursday morning where we had just found the inverse sine, inverse cosine, inverse tangent all give us this angle theta. And I had asked you to think about the other 5 parts of this problem that we were going to start class today with filling these in. So let's just make sure that we know what's happening here. So for example, on part E, it said we don't want to know what theta is. We don't care about that, but can we find the tangent of theta? Well, definitely we can. If this is theta, then this is the vertical and this is the horizontal. And so we end up with tangent of theta equal to the vertical over the horizontal, or 5.33 divided by 10.62. I would go ahead and calculate those values, but it seems like an unnecessary time waste at this point because you guys know how to do that in the calculator. And then likewise on parts A through D. So parts A and B asked you to find the sine of theta, and we can identify we've got the vertical and the radius, the vertical and the radius. And so the sine of theta on part A is just 3/5, and the sine of theta on part B is just 1.92 over 5.43, whatever that works out to be. In part C, they asked us to find the length of BC. Well, that's this length right here, and we don't really need a trig function to do that. We should be able to just use the Pythagorean theorem by identifying that we have 2 legs and the hypotenuse. We should be able to say a squared plus 2.4 squared is equal to 4 squared. And so we end up with a squared equals 16 minus, let's see, 2.4 squared. I don't know what that is off the top of my head, so I'll just leave it for right now. And then we take the square root of both sides, and A ends up being, if I'm not mistaken, I think it ends up being 3.2. Let me take a peek at section 6 just so I don't have to pull that calculator up right now. Yeah, 3.2 is what that ends up being. Okay, part D, they asked us to find cosine and sine. So this one, the triangle is oriented backwards of the way that we're thinking about it. This looks like a second quadrant angle, only this value is not negative the way we would expect it to. Since we're dealing in a triangle, we're not really looking at directional distance. It's not in the coordinate plane. So we've got the vertical distance, the horizontal distance, and the radius. And so the cosine of theta is equal to 8.3 over 10.6. This marker's not working very well this morning, is it? Let's try that again. 8.3 over 10.6. And the sine of theta is 6.6 over 10.6, whatever that turns out to be. Those are just basic ideas. The thing I want you to keep in mind here is that when we're looking at something like the sine of theta is equal to some value, the input of that is an angle, the output is a ratio. So if they're asking us for the sine of theta and we don't know what theta is, as long as we have the components of that ratio, we should be able to find out what that is. As I walked around the room in all of my classes, I noticed that a lot of people wanted to say the sine of the ratio is what we were looking for, and then you ended up with the sine of something very odd. Remember that what goes into the sine function is an angle, and if you do not have that angle, then you cannot plug it into the calculator and figure out what the sine is that way. Instead, you have to look for the ratio, or you have to find the angle another way. All right, so what I really wanted to focus on today was this page right here. This is Module 8, Investigation 1, problem number 2 in particular. We have this triangle over here to the left, or excuse me, to the right. And so we want to find sine of alpha, cosine of alpha, tangent of alpha, etc. And then also the angle measures for alpha and beta. So I'm going to encourage you to pause the video at this point and see if you can find those values on your own, and then restart the video and I'll walk us through them. So hopefully you have done that. You have paused the video and looked on your own. The first thing I'm going to need is I'm going to need to figure out what this hypotenuse is. So I'm going to go 2 squared plus 6 squared should be the hypotenuse squared. And so I've got 4 and 36, so that's 40. The square root of 40 should be my hypotenuse here. And I'm just going to leave it as a square root of 40. You could say it's 2 rad 10. You could round it to 6.63 something, I think. But for now, I'm going to leave it as rad 40. So if I'm looking from the perspective of alpha, then what I've done is I've tilted this triangle up so that I can look at it from this perspective. Here's my right angle, which means that I've got 2 here and 6 here and rad 40 here. Okay, so that means that I can see the sine of alpha is 6 over rad 40, and that the cosine of alpha is 2 over rad 40. The tangent of alpha would be 6 over 2, which simplifies quite neatly to 3. The sine of beta, if I look from this perspective over here, we've got vertical here, so we've got 2 over rad 40. Cosine of beta would be 6 over rad 40. And then the tangent of beta is 2 over 6, or 1/3. Okay, so let's take a look at how do we find the angle here. Now we're in a triangle. We're not in a circle, so I'm gonna put my calculator in degree mode, and I'm gonna look for alpha or beta, and then I can find the other one from the first one. So the simplest thing to do here, to me, seems to take one of these guys up here and apply the inverse, right? So for example, if the tangent of alpha is 3, then the inverse tangent of 3 should be alpha. And if I plug that into my calculator, inverse tangent of 3 then I get 71.57 degrees. Okay. Now I could use that same policy to find angle beta, but instead I think what I'm going to do is I'm going to recognize the fact that the interior angles of this triangle, right? If I've got the interior angles, all 3 of these angles of this triangle, they sum to 180. Well, I've already used 90 degrees up in the right angle, which means alpha and beta have to sum up to 90 degrees themselves, because I've already used up 90 in the other corner. So alpha plus beta should be 90. So I should be able to say that beta is 90 minus alpha. So if I do 90 minus that previous angle, then I end up with 18.34 degrees. Okay. Now I want to pause right here and kind of point out that we have a pattern up here in these 6 trig functions that we found. It seems like a lot of numbers, but it's not really a lot of numbers. It's a repetition of a lot of numbers. So for example, the sine of alpha is equal to, the cosine of beta. Those are both 6 over rad 40. And likewise, the cosine of alpha is equal to the sine of beta. So what we've got here is the first of some identities. We have cofunction identities. And I want to switch over to this page and talk about those for just a second. If we look at this triangle, oh, I'm still in highlighter mode. If we look at this triangle, our right angle is up here. And we say maybe this is alpha, this is beta, I'm going to call this B and this A and this C. Then we know that the sine of alpha, right, if we're looking from this perspective, there's the vertical and the radius, so we've got A over C. And we already recognize the fact that that's the same as the cosine of beta. But we also said that alpha and beta together sum to 90, so this is the same thing as the cosine of 90 minus alpha. And that's what's known as a cofunction identity. Likewise, the cosine of alpha is going to be b over c, which is equivalent to the sine of alpha, the sine of beta, which is the cosine, the sine of, 90 minus alpha. So these are cofunction identities. When we are able to say that the sine of alpha is equal to the cosine of 90 minus alpha, these are cofunction identities. So I'm going to leave it there for this video.